Somewhere in a high-security compound in Shenzhen, engineers work under fake names. Their phones are restricted. Many of them sleep on site during the work week rather than going home. Different teams are kept deliberately isolated from each other so that no single person knows the whole picture of what they're actually building. According to a Reuters investigation published in December 2025, what they were building is one of the most closely guarded machines in the entire technology world, an extreme ultraviolet lithography system, the exact tool that years of American export restrictions were specifically designed to keep out of China's hands. For 2 decades, this single category of machine has been the ultimate choke point of the global chip industry, made by essentially one company on Earth. If China has genuinely built a working prototype of its own, using recruited engineers and salvaged parts, the entire foundation of Western chip export controls just cracked. So what exactly did they build? And is it as close to working as the reports suggest? Let's break it down. To understand why this story is such a big deal, you need to understand what an EUV machine actually does, and why almost nobody on Earth can build one. Making an advanced computer chip starts with printing an incredibly precise pattern onto a silicon wafer, a process called lithography. To draw features small enough for today's most advanced chips, you need extremely short wavelengths of light, specifically extreme ultraviolet light at 13.5 nanometers. Generating that light reliably, focusing it with mirror precision measured at the atomic scale, and using it to expose a wafer without destroying the equipment in the process is considered one of the hardest engineering problems humanity has ever solved. For over 20 years, exactly one company in the world has been able to build and sell these machines commercially, ASML, based in the Netherlands. A single EUV scanner contains more than 100,000 individual components, many supplied by other highly specialized companies, most notably Germany's Zeiss, which makes the ultra-precise mirrors these systems depend on. Since 2019, the United States has restricted ASML from selling its most advanced EUV machines to China at all, treating this single point of control as the most powerful lever in the entire chip export control regime.
According to Reuters' investigation, sources familiar with the project say the Shenzhen prototype was completed in early 2025 and has been undergoing testing since. The scale of the operation is significant. Reporting describes involvement from Huawei, the state-backed firm SciCarrier, and a coordinated web of research institutes, with more than 3,000 researchers working across different parts of the lithography, deposition, and etching supply chain. To build the machine, teams reportedly salvaged components from older ASML systems, sourced parts through secondary markets and intermediaries, and used export-restricted components originally made by Japan's Nikon and Canon. Reuters reported that auctions of used ASML equipment inside China continued as recently as October 2025. A dedicated team, reportedly made up largely of recent university graduates, has been assigned to the painstaking work of disassembling and reassembling components to understand exactly how they function, with each desk reportedly filmed to document the process and bonuses paid out for successful reconstructions.
Salvaged hardware only gets you so far without the expertise to understand it, and this is where the story gets most striking. According to multiple reports, China's effort has actively recruited engineers who previously worked at ASML itself, in some cases offering signing bonuses reported at up to roughly $700,000, along with generous housing subsidies. One name that comes up repeatedly across reporting is Lin Nan, previously head of light source technology at ASML, who now reportedly leads a team at the Shanghai Institute of Optics and Fine Mechanics. That team has been credited with filing 8 separate patents related to EUV light sources within an 18-month period, and with publishing research reporting a light conversion efficiency of 3.42%, a meaningful technical benchmark, since higher conversion efficiency means less energy is required to generate usable EUV light at production scale. Analysts studying the effort describe this as a hybrid strategy,
combining brute force reverse engineering of physical hardware with direct recruitment of the specific human expertise needed to actually understand what that hardware is doing.
One detail that separates this from a single lucky breakthrough is that China appears to be pursuing several different technical approaches to generating EUV light at the same time, rather than betting everything on one method. Reports describe at least 3 distinct teams working on different light source technologies. A team at Harbin Institute of Technology working on a laser-induced discharge plasma method. The Chinese Academy of Sciences team using laser-produced plasma based on a solid-state laser, the same core technology ASML itself uses, and a team at Hefei Lumiverse Technology exploring an entirely different high harmonic generation approach. Running multiple independent technical paths in parallel is expensive and resource-intensive, but it's also a classic sign of a nationally coordinated effort willing to absorb the cost of failure on some approaches in exchange for a higher chance that at least one path eventually works. Some analysts have compared the scale and secrecy of the overall effort to a Manhattan Project-style national mobilization, a comparison Reuters' own source reportedly uses internally within China as well. Here's where it's important to separate a genuine milestone from a finished weapon. According to Reuters reporting, the Shenzhen prototype is operational in the sense that it can generate EUV light and is undergoing active testing. It has not yet produced a single functional, usable computer chip. The machine reportedly occupies nearly an entire factory floor, significantly larger and cruder than ASML's commercial systems. The single hardest unsolved piece, according to multiple reports, remains precision optics, the ultra-smooth, atomically precise mirrors that reflect EUV light onto a wafer with almost no loss or distortion. Germany's Zeiss is currently the only company on Earth that can reliably manufacture these mirrors at the tolerances required, and China's domestic attempts reportedly still lag well behind. Photoresist chemistry, the ultra-pure, light-sensitive coating that actually forms the pattern on the silicon, presents a similar story. A Tsinghua University team announced a promising formulation breakthrough in mid-2025, but a lab result is a long way from the purity and consistency required for high-volume commercial manufacturing.
It's worth being precise about the actual timeline being discussed, because the headlines and the underlying sourcing don't always match. Chinese authorities have reportedly set a public goal of producing working chips using this technology by 2028. But according to Reuters' own sources close to the project, 2030 is considered a more realistic target internally. ASML's own CEO, Christophe Fouquet, has publicly stated that China would need, in his words, many years to develop functional EUV technology of its own. Some industry watchers have pushed back on that level of confidence, noting that a fully assembled, light-generating prototype existing at all is a more significant milestone than most Western analysts expected this early. Others remain skeptical, for good reason, pointing out that going from a lab prototype capable of generating EUV light to a commercially reliable, high-volume manufacturing tool has historically taken the global industry decades of accumulated engineering, not years.
Even a partially successful EUV effort would have consequences well beyond one factory in Shenzhen. Chinese chip designers like Huawei and Baidu's chip subsidiary Kunlunxin are currently physically limited in how advanced a processor they can design, because without EUV-capable manufacturing, they're stuck using older, less precise lithography techniques that require multiple exposure passes to approximate what a single EUV pass can do. That physical ceiling is a major reason Chinese AI chips have generally lagged behind the most advanced offerings from companies like NVIDIA. If China's domestic EUV effort eventually becomes commercially viable, even at a smaller scale or lower yield than ASML systems, it would directly attack the specific technological choke point that export control policy has depended on for years. It wouldn't need to match ASML's most advanced machines to matter.
Even a domestically produced machine capable of reliably printing chips several generations behind the absolute cutting edge would meaningfully reduce China's dependence on foreign suppliers for a huge share of practical, real-world chip production.
Here's how I'd frame this one. The headline, "A secret working EUV prototype," is genuinely remarkable, and it's easy to see why it generated as much attention as it did. But the more important detail is buried in the same reporting that broke the story. This machine cannot yet make a usable chip, and the hardest unsolved problems, precision mirrors and ultra-pure photoresist chemistry, are exactly the parts of EUV lithography that took the global industry the longest to solve the first time around. That doesn't make this a non-event. A country secretly assembling a functioning, light-generating EUV prototype years ahead of what most Western analysts expected is a meaningful signal on its own, regardless of when or if it ever reaches full commercial production. What this story really shows is the same pattern we keep seeing across Chinese semiconductor efforts: national-scale coordination, aggressive recruitment of the exact human expertise export controls can't restrict, and a willingness to run multiple expensive parallel approaches rather than betting everything on one. Whether that adds up to a 2028 timeline, a 2030 timeline, or something slower still is genuinely uncertain. What's no longer uncertain is that the choke point export controls were built around is under real, sustained pressure for the first time in over 2 decades.
So here's the real question. If China's EUV effort lands anywhere close to its 2028 to 2030 window, does that mark the end of Western chip export controls as a meaningful strategy? Or does the West simply move the goalposts to the next generation of lithography that China still can't touch? Let me know what you think in the comments. And if you want more grounded breakdowns of the secret projects and technical breakthroughs reshaping the global chip war, subscribe, because this story is nowhere near finished.